Right, so here's the beginning of part two for this. Um, so, we were talking about the body. So let's put up this blank one. Does anybody know what this is the general form of? Something pretty damn important.
What is R?
There are 20 versions of this,
Okay.
and the only thing that really changes is the R. So if I put just an H here, it's the most simplistic version. It's called glycine. Lysine, cysteine, methionine, tryptophan. Any of those? What?
They're sugars.
No, they're not.
Uh,
Amino acids.
um,
So protein structures are composed of just a bunch of these guys stuck together. So imagine you're building those large protein structures. You've got 20 different options. So think about you've got 20 different Legos and you start mashing stuff together. And so that's what all your proteins are. So this is super important because this right here is an organic acid. C double bond OH is an organic acid, and this is a base. So now this is easy to see why this is an acid. How come the right side's an acid? Arrhenius could answer this.
the right side we're talking about?
Yeah.
It has an electron to donate.
No,
No.
the right side. This thing right here is an H plus and it can leave. That's why this is an acid. But Arrhenius wouldn't be able to define this as a base because there's no OHs around, but that can actually attach right there. And so this is donating electrons. This is accepting electrons. All right. So what is in your body that acts as the base? Nitrogens. Why? Because they're attached to a whole bunch of different things. They've got a lone pair of electrons on them. And so they'll make bonds where they offer up a pair of electrons. Is there anything super important besides proteins and amino acids in your body that use this? Yeah, your DNA. The hydrogen bonding cross section that holds the two strands of DNA into a double helical structure. It's those electrons on that nitrogen do that. So when this thing gets redrawn, it looks like this. This side is positively charged. Yeah, sorry. And this side is negatively charged. And then there is something here. It actually chemically reacts with itself to do that. And so it performs an acid-base reaction with itself. That's what makes this thing soluble because it's got a positive and negative side on it itself. All right, so let's go back. Okay, so we've got Arrhenius' theory that says H plus goes up, it's an acid. OH minus goes up, it's a base. We've got Bronsted-Lowry that say, hey, H pluses can't exist, it's got to be a hydronium ion. Something comes in and disassembles it, and they're saying that water molecules come in and pull stuff apart. And so what you end up with is something donating an H plus or a proton and something accepting a proton. So their definition was anything that accepts the proton is a base, and anything that donates the proton is an acid. So there's Bronsted-Lowry's definition. And then we go to Arrhenius, Lewis, who says we need to be more encompassing in our thinking. And so he says, instead of acids being H pluses and bases being OH minuses, we don't need to talk about that. What we need to talk about is what really matters is a chemical bond is formed with electrons. So let's start there. So anything that donates some electrons to make a bond, that's a base. And anything that accepts those electrons to form a bond is an acid. So we get much more broad in our definition. So what are some definitions of Lewis acids? So a Lewis acid is something that accepts electrons. So any positive ion would be a Lewis acid. Why? Because if it's positive, it would be happy to accept some electrons. Anything having less than a full octet in its valence shell, like sulfur or phosphorus. We talked about how sulfur and phosphorus violate the octet rule and can have 10 and 12 electrons. So if they can accept more electrons, then that makes them an acid. The polar side of any double bond, we'll get to that when we talk about organic stuff. And then anything that's got expanded valence shell. So all of these things are things that it can accept electrons. On the other side, anything that's negative has extra electrons, so it could donate those electrons to form a base. Anything that has more than one or more unshared pair of electrons. So a water molecule has two unpaired unpaired electrons, so that they could form a bond with. And nitrogen's got one. The other side of a double bond, polar double bond, again, we'll talk about that when we get to the organic stuff. And then anytime a double bond is present. So do you remember why double bonds were so chemically reactive?
Above and below.
Yeah, so I've got electrons above and below a flat structure. So these guys are in a flat structure, all in the same plane, and above them and below them, I've got these excess electrons. So if a Lewis acid is the ability to donate electrons, a double bond is a great place to get electrons because they're super available. They're on top and bottom. I can run in, there's like this entire top and the entire bottom of the molecule are places that can be run into. So when we're talking about molecular collision theory, it's easy for them to hit those electrons. So that makes those double bonds super reactive. And since they're reactive because they're donating electrons, that forms a Lewis acid. So that makes those double bonds a Lewis base because they're donating electrons. Okay. We're going to move on to some kind of definitions. So there's something called the strong acid and something called the strong base. Does anybody remember strong and weak electrolytes? Well, what did we mean by strong and weak electrolytes?
Solubility, degree of solubility.
Degrees of solubility. So a strong electrolyte did what when it went into water?
Ions.
Nothing stuck together. The table salt goes in, all the NAs and all the CLs separate unless I've reached the saturation point for that solution. So it's the same situation for strong acids and strong bases. Any strong acid, when it goes into water, fully separates. It's fully soluble. And same thing with the bases. So there are 7 strong acids. And I'm not right here. All right, here they are. So HCl, HBr, and HI. So those are the anions are right on top of each other in the halogen column of the periodic table. Then we've got nitric, sulfuric, chloric, and perchloric. So when those guys enter water, the H's come off. It's a little bit of a misnomer with the sulfuric acid because there are 2 H's. Only one of those H's come off. The second one, when it comes off, it's not a strong acid, it's a weak acid. So there are literally millions of acids. 7 of them are strong. All of the rest of them are weak. So what was the difference between a strong and a weak electrolyte? What happens with the weak electrolyte? Tell me again what strong electrolyte meant.
Full separation.
So these guys have full separation. All of the H comes off no matter what. So what would weak acid mean? We use this in the equilibrium examples. almost all of them, I was like 1,337 or 34 or 38 or 48, whatever. Over 1,300 of these guys, when they go into water, say stuck together as HF. And the other, then there's for every one H plus and F minus. So they like to be stuck together. Okay. So all other acids are this type, where the H usually stays stuck, but it can come off. So this will provide ions for electrons to flow through pure water. And this will provide H pluses to increase the H plus ion concentration to make this solution more acidic, but not as much at the same concentration as if you put in any of those strong acids. Those strong acids fully separate, where over here you only get, like 1 out of 1,000 separating out. Okay, so let's roll back up here and talk about some properties for acids and bases. Okay, so properties of acids and bases. They produce OH, H3O pluses in water, so hydronium ions. So we're not going to say that they make H pluses in water because they don't. They make these hydronium ions. They turn litmus from blue to red. Does anybody know what litmus is? Litmus test is, and then that gets used when someone says, well, it's a litmus test. If they're not talking about chemistry, what do they mean? It's go, no go. There's only two options. It either is this or it's not that. So in popular verbiage, litmus test simply means this thing is or it is not. And in chemistry, litmus is something that is showing you that it is an acid or it is a base. And litmus is a dye pulled from cabbage. So it will be red or kind of pinkishy colored. And that will be an acid, or it will be blue. And if it's blue, then it's a base. So if I've got some red litmus and I put it in acid, nothing happens. If I've got a piece of red litmus and I put it in a base, it'll turn blue. They will make double replacement reactions with solid oxides. So it will take rust and turn it into salt. If you add an acid to rust, you'll get a salt. So if you put it on like regular old rust, iron 3 oxide, you'll get iron 3 chloride and water. Double replacement reactions with hydroxides, you're going to neutralize both of them. We should talk about that for a second. What's more dangerous, an acid burn or a base burn? You had 10 moles per liter concentration hydrochloric acid and you dumped it on one arm, 10 moles per liter sodium hydroxide concentration and you dumped it on the other arm. Which one would hurt worse? They're exactly the same. They're both damaging in their own way, but they're both tissue damaging for sure. They're both caustic. But they're easy to take care of, right? If you have acid all over your hand, you put a base on it, neutralize it.
Like the salt water, if you have a base on your hand, like if you spilled Drano all over yourself somehow, what could you do? You could cover yourself in vinegar. You could throw up on yourself, whatever. Those things would work. You could pee on yourself. Would work. Probably not your first option, but there's enough acid there.
To get salt and water out of that. And then you have a double replacement reaction with carbonates and bicarbonates. So carbonates or hydrogen carbonates, you get a salt and CO2. So the moment you mix in acid, carbonates or hydrogen carbonates, what
is immediately like instantaneously you'll see what happened. Carbon dioxide gas, right? So if you mix an acid with any carbonate or hydrogen carbonate, immediately you'll get bubbles. Mixing vinegar and baking soda, throwing up on baking soda, it would bubble immediately.
So that's why an antacid removes excess acid in your stomach because it neutralizes it, turns it into carbon dioxide and a salt and some water as well. But the acid is no longer there. And then if I take an acid and I put it on water, or sorry, on metal, I actually get hydrogen gas and a salt. And depending on which metal I'm talking about, the reaction can be super violent or kind of violent or not actually work at all. If it goes on some metals, no reaction happens. Can you, from what we've talked about on the periodic table, can you tell me which of those metals don't react when I put them in acid? If you had some of those metals up there, which metals would you not want? The ones that we've made money out of and jewelry out of
Silver and gold.
and copper. So you can put those guys in vinegar, nothing will happen to them. You can create a solution that will dissolve gold and silver and copper. If you mix hydrochloric acid and nitric acid together, that's the term for that is royal water, aqueous regia, and that will dissolve gold. And that is actually how Niels Bohr saved the gold from his Nobel Prize when the Germans came to his lab. He left, but he couldn't take it with him because he was worried that if he had a medallion of gold on him, that someone would steal it from him. So he dissolved it in a mixture of hydrochloric acid and nitric acid, and then he put it in a innocuous looking Erlenmeyer flask and stuck it on a shelf and put a label on it. It didn't mean anything to anybody. When the Nazis raided his lab, nobody noticed that that was a container filled with gold water. And then he just reconstituted and sent the gold back to them and had them remint it. It was kind of cool. So if you were to take acid and you put it on water, or sorry, on metal, it will dissolve those metals as long as it's not the metals at the bottom of the activity series, which we'll get into at another time. But for us, we're just going to be thinking about gold, silver, and copper. Those will not dissolve. But if you were to put acid on metal, like iron or steel or something like that, you will get bubbling. The bubbling will be hydrogen gas, and then it will rust into well, you actually get a salt out of that. It's kind of how some batteries work. Like the Aliens movie, I don't know if you remember that the aliens' blood is acidic and it would like dissolve deck plates and stuff like that. So possible, sure. Probably not, but definitely possible. These are the three most common acids that you'll find in the lab: hydrochloric acid, nitric acid, sulfuric acid, and acetic acid. And those are the maximum concentrations that you can get. If you try to put more hydrochloric acid into a solution that's already 12 molar, it will leave as a gas. It cannot be more concentrated than that 12. And the same thing goes with the 16 and the two 18s. Although the bottom one is interesting because you can have 18 molar and there's no water present. It's literally just straight acetic acid with no water in it. And I showed that video of that guy using concentrated acetic acid and electrolyte, the light wouldn't shine. Then he added a little bit of water and then the light came on a little bit and he added more water and the light came on fully. So it's called glacial acetic acid. I actually don't know why, but when it's in its fully concentrated form, that's what it is. So that would be 95 more times more concentrated than vinegar. All right, so what about some properties for bases? They produce hydroxide ions. They do the opposite to litmus. So if I've got a piece of red litmus paper and I put it in a base, it turns blue. If I've got a piece of blue litmus paper and I put it in a base, it doesn't do anything at all. It feels slippery when you touch it. Does anybody know why it feels slippery? You guys actually did the chemical reaction to prove that it does feel slippery last quarter. You made something, a common something or other. You made soap. So what's on your skin, on the exterior of your skin? Oil. If you don't have oil on your skin will crack open as water dissipates out of it, and you'll have all kinds of infections. It'll be a bad situation. So you're covered in oil. And when you touch a base, that base and that oil come in contact with each other and they make what? What'd you guys make?
So,
Soap, right? You took oleic acid, right? Just vegetable oil, and you mixed it with sodium hydroxide last quarter, and what'd you make? Soap. So if sodium hydroxide touches your skin, it feels slippery. Why does it feel slippery? What did you just make? Soap. So if you touch a base, you literally make soap out of the oil that's on your skin. So your skin will be very clean because you literally just made soap out of the oily thing, but it's also just removed all of the oil off of your skin. So you should replace that as quickly as possible. But if you're like covered in motor oil or I don't know, wheel grease. God, wheel grease is the worst. Like what you put in around the axles for a bike or like our tractor ball bearings needed more. I got some of that stuff on my skin. I could not get it off. I literally went into the bathroom and I got some Drano and I put a little bit of it in my hand and rubbed it around. I got rid of it. But then I immediately rinsed off and then covered it in working hands because it got removed everything. Okay, so feel slippery because it makes soap. They taste bitter. So most of the time we are not happy with bases as food. Does anybody know why? Bitter isn't a pleasant flavor for us. What do you think your body is telling you when you eat something and it tastes like garbage? What? It's rotten, or how about be more general than just it's rotten? It's bad for you, toxic in some way. So you eat something and you're like, oh, that's like moldy bread. Like you didn't see like on the bread you just put in for toast, you cooked it on the bottom side, there was a tiny bit of mold you didn't notice, and you immediately are like, mold. Don't eat it because it can make you sick. In some way that could be toxic. So the same thing happens with things that are bitter. What does the outside of an orange peel taste like? Do you want to eat the outside of an orange peel? No, it's bitter. The orange peel itself isn't going to hurt you, but in general, things that are bitter have been poisons to humans. So when we bite into something and it's bitter, we're like, spit that thing out, get that out of your mouth. We consider that thing to be a poison, and many poisons are actually bitter. So they are bases, and so we don't appreciate that. And so I mean, there are some bitter foods out there that people like, but very, very few. We will eat the hell out of some acids. Like we love acid. We love our ketchup, mustard, vinegar. Any Sour Patch Kids. I mean, vitamin C is as acidic as it gets as far as biological molecules or molecules with biological activity. And we have no problem eating that stuff. But we know immediately if you try to take something that's bitter. Okay, so neutralizes an acid solution. So we already talked about that with the one above. Breaks down fats and oils to make soap. So if you like Formula 409 is a cleaning solution that people use in the kitchen. What kind of solution do you think it is, an acid or a base? Formula 409 is a pretty common cleaning solution. Same thing with Comet or bleach. Those are all things that people use to clean kitchens. Are they acids or bases? They're all bases. What is it that they're trying to clean? Oil. So when you put Formula 409, Comet, or bleach on bacon grease that's splattered out of the pan that you made,
what happens to the bacon grease? Last bullet point. So you've got this thing that you can't clean up. And what do you do to it? I turn it into soap and now I've got a cleaner. I'm actually able to clean my stovetop with the thing that was messing my stovetop up because I just turned it into soap. So that's why all of those cleaning solutions are all bases, even like Simple Green and all those things. They're just different versions, more palatable molecules to the sewage infrastructure or like a septic system. Like if you're on septic, Simple Green is probably your best choice because it won't kill all the bacteria in your septic system, which you definitely don't want them to die. Unless you like the smell of poop, human poop specifically. Okay. So the list of strong bases is not here. It's supposed to be right there. Where did it go? It's super easy. Take all the group 1 metals and attach an OH to it. Lithium hydroxide, sodium hydroxide, potassium hydroxide, cesium hydroxide, rubidium hydroxide. Probably not any francium hydroxide because there really isn't any francium. But you're most commonly going to come in contact with sodium hydroxide and potassium hydroxide, possibly some lithium hydroxide, but probably not because it's lithium is used for a bunch of stuff now, obviously. Batteries, yeah. I mean, we honestly should be using sodium, but they haven't perfected that technology. I mean, it's problematic to find lithium, right? Do we know how we do that? Drill holes in the ground and pump water in it and the salts come out and then you separate out or we could just spend $1 billion on research and come up with the sodium battery because that's a hell of a lot easier to get our hands on, but we just haven't done that yet. I mean, there's a reason to use lithium. When we get to electrochemistry, it'll be obvious to you, but not a good enough reason, in my opinion, based off of how much it costs and how hard it is on the environment. I mean, it's not like a regular mine, like a copper mine or an iron mine. Those are devastating. Okay, so what about salts? Salts are important to acids and bases because when you combine the two of them, you get a salt. So they're obviously super important. The salts that we use, we need a certain amount of them because they allow our body to perform osmotic functions. Your heart only beats because of certain concentrations of sodium, potassium, and calcium ions. If I don't have those in the correct concentrations, your heart goes into AFib and you die. It's a good way to get things that we want into the bloodstream. Sodium, naproxen sodium is the third non-steroidal anti-inflammatory, aspirin, Advil, and Aleve. And it's naproxen is the molecule you need in your bloodstream, but it doesn't want to be solubilized. So they make it, they attach a sodium to it, turn it into sodium naproxen. So then when the sodium hits water, it comes off and now the naproxen's a negative ion. And so it's charged. So water molecules can attack it. So we're not going to make a drug that I can't turn into a salt because you need it to be solubilized to get into the bloodstream because that's the body's distribution method. They're ionic compounds. Salts of weak acids and bases form buffers. And so that's super important to us. Keeps our pH of our bloodstream constant. And we're going to spend a lot of time talking about buffers in the future, probably Wednesday. And then we also have the hygroscopic effect of many salts that form hydrates. So we've seen the hydrate thing several times, and calcium sulfate with those two water molecules on it, that's all around us. That entire wall right there is that stuff, gypsum. What's another name for gypsum? The construction name for gypsum.
Sheetrock? No.
Sheetrock or drywall. Why is there so much sheetrock all over the place? I mean, it's kind of a pain to work with, right? You can't screw anything into it. I mean, you can screw very small things into it, but then it disassembles. Like why did they choose sheetrock
this calcium sulfate dihydrate as the thing that we use for separating rooms in buildings. I'll tell you, it's a safety thing. It makes, I was on city council in the Dalles for 4 years, and we actually had to have a guy gut his house out because he violated code. And every house in his house, every wall in his house was made out of wood. It was beautiful. And it was also a code violation. Why? Why can't you have wood walls in your house?
Super flammable.
Super flammable. If a fire starts in the kitchen, everything in the house is flammable. So why do we make things out of drywall? Walls out of drywall.
Hard to burn.
It's a salt. Salts are not flammable. That wall is not flammable. There is no way a flame can get through that. There is, obviously, because buildings burn down. The way to do it is you burn the paper off, right? Like if you all know what drywall looks like, it's coated in this paper substance. And once that paper burns, then the drywall, the gypsum kind of flakes off, and then you can burn the other side. But you got to get through the wall. And this burn time on a regular wall, gypsum wall, which is a ½ inch, is a half an hour. So if a fire started in this room, it'd be a half an hour before it got through that wall to the other side. But probably more like an hour because there's insulation in between the two of those, and there's no insulation, but there's 2 drywalls because there's power and pipes running through there. So it'd be an hour if I started a fire in here to get through that wall. And at that guy's house, that everything was made out of wood, it'd be about 5 minutes. So that is the reason. And people are like, well, he accepted the responsibility, and so whatever. I'm like, that's fine, but what happens when he sells the house? That person didn't accept that responsibility. So it's basically looking out for post-consumer usage as far as code violations go. You know what? I'm gonna stop right here. And yeah, that's it. We'll go to lab. Oh, tell me I did not. Okay, good.